You know, it's crazy, but 9 out of 10 students get binary to dinary conversion wrong in exactly the same way, and it just quietly drains their grade right out from under them. So, welcome to The Explainer. We're skipping the slow intros today because, honestly, there's just too much at stake here. Let's look at this classic mistake right now so you never have to make it.
Picture this. A student sees the binary string 10011 and they just rush to convert it. They misalign the column headers, or maybe they just guess the place values. And just like that, perfectly good logic crashes into a 0 on the exam paper. It's absolutely devastating. But the good news? It is entirely avoidable.
Okay, so here's the fix. The binary system uses base 2, right? In an 8-bit system, your column headings reading right to left are always 1, 2, 4, 8, 16, 32, 64, and 128. It's just doubling every time. So map that 10011 carefully starting from the right. Then all you got to do is add up the columns that are switched on with a 1. So that's 16 plus 2 plus 1, which gives us 19. If you lock in this visual alignment, you literally can't fail these questions.
Now, understanding the technical math is really only half the battle. Communicating it exactly how the examiner expects, that's the whole shebang. To secure top marks, you need a solid 4-step framework. State the core concept, provide your evidence, apply scientific reasoning, and finally, use precise examiner wording. This framework is essentially your shield against what we call the generic answer trap.
So what does that mean? Well, you absolutely must elevate your everyday language into sharp, technical reasoning. Saying something like, the CPU is the brain of the computer, that's a floating abstraction and it earns exactly 0 marks. Compare that to saying, the CPU executes instructions using the fetch decode execute cycle for this specific robot. See the difference? 1 mark requires 1 distinct technical point. So whatever you do, don't waste time repeating generic ideas.
And that brings us to the 3 layers of mastery. Layer 1 is just your everyday language, like knowing a system is running slow. Layer 2 introduces actual technical vocabulary, but Layer 3, that's where you secure the A star. That's about shaping your knowledge directly to the mark scheme. If a question asks about a smart home CPU, you can't just write about a generic CPU. You have to explicitly link the processing to the smart thermostats in that exact scenario.
When you're explaining what that CPU actually does, you're going to need the fetch, decode, execute cycle. Now, the absolute secret to full marks here is logical sequencing. You identify the task, and then you explain the process chronologically. Fetch, decode, execute. Make it so clear that anyone could follow it perfectly. And finally, anchor it right back to the scenario. No memorized lists, okay? Just pure applied logic. And hey, this structured logic applies perfectly to data transmission too. There are 3 distinct modes you need to master chronologically. Step 1 is simplex, which is strictly one-way transmission. Step 2 is half-duplex, where data alternates directions but never at the exact same time. And step 3 is full duplex, which is simultaneous, 2-way transmission. Let's put that into perspective. A traditional radio broadcast? That's pure simplex, just sender to receiver. Walkie-talkies are half-duplex. Data flows in both directions, but you definitely have to take turns. A modern phone call, though, is full duplex, with a simultaneous 2-way flow. The crucial takeaway here is to avoid vague terms like Wi-Fi or Bluetooth. Using precise terms about the direction and timing of the data flow is exactly what wins you those marks. Now, you might be wondering, how do you actually lock all these complex concepts into your long-term memory? It's all about the 3-pass revision cycle. Pass 1, secure your definitions so you never mix up your terms. Pass 2, rehearse your step-by-step explanations, ideally using diagrams. And Pass 3, exam adaptability. Practice applying that theory to wildly different scenarios so you can confidently justify your choices. Take a notoriously tricky topic like parity error checking. You can master this using a 4-prompt memory structure. To construct a flawless answer, just ask yourself 4 things. What is the digital problem? How does the technical sequence work? Where is this taking place, like maybe a banking network? And why is it advantageous compared to other methods? If you can answer those 4, your explanation is pretty much unbreakable. And that exact same reasoning path applies directly to checksums and check digits. You really have to move beyond rote memorization here. Start down at layer 1 with the practical problem, like a barcode scanning incorrectly. Then, elevate to layer 2 by integrating your technical vocabulary. And finally, hit layer 3, the exam-shaped response. Classify the concept, order it chronologically, and apply the specific context. Which brings us to a really dangerous trap, the floating abstraction. If an exam asks for a network advantage and you just write faster load times, well, that's a floating abstraction. I mean, faster for who? Compared to what? Instead, write something like faster load times for the school's intranet when students download large video files. Every single advantage has to be explicitly linked back to the scenario. No exceptions. Believe it or not, this even applies to HTML programming. You have to separate mere description from actual structural explanation. Don't just name drop an HTML tag. Explain how it works and exactly why it matters in that specific web layout. Run it through your 4-question self-check to order your logic sequentially before you even mention the visual result on the web page. If there is one golden thread pulling all of this together today, from binary math all the way to HTML, it is absolutely this: anchor your answers to the scenario nouns. Generic answers lose marks. When you see a scenario about a retail store or a delivery robot, those nouns are your best friends. Integrate them deeply into every single explanation you write. All right, let's put that sharp, analytical mindset to the ultimate test. Can you spot the single fatal error in this logic gate sequence in under 10 seconds? Trace the inputs, check the conditions, and whatever you do, don't get trapped by an easy assumption. You've conquered the language traps in this explainer today, but what happens when the exam throws a massive, complex algorithm trace table right at you? Well, that is exactly what we're going to be decoding next.